Hello, my dear students. This will be the video for today. Then that there will be specific um task that you will begin to do at the end of the session. So since I know the situations that it is raining, so we cannot have our online meeting. So due to the constraints that everybody is actually um, or they're not capable to join the online meeting. So I am anticipating that you're having a bad signal due to the typhoon as well. Since then, way back, they call this one um, typhoon Tino. So I am still anticipating that other student cannot join the meeting. So therefore, I will begin to just create the video for our class instead, in order for you to really understand that one. It will be easy for you to understand them because you can definitely play the video over and over again. Okay, so our topic for today, this will be the last topic for the trees data structure, since we will not begin to discuss everything. Um, so this is actually all about expression binary tree. So talking to expression binary tree, let's actually define that one. What is this? So when we say binary expression binary tree, that is a binary tree used to represent mathematical expressions. The internal nodes of the tree contain operators, while the leaf nodes hold the operands, which is the values or the variables. That means to say, um, once we can construct a specific expression binary tree, since there will be a infix notation pertains to that. So what is infix notation? Such as the, for example, a plus b. There is a operands. When we say operands, the values, and there will be an operator. It could be in between the two. So that's absolutely called the infix notation. So we will begin to deal with the expression tree pertains to that infix notation later on. I'll begin to illustrate in different video on how to work on in regards to those infixation. There will be two ways in how to to get this one. We can also use the stack data structure, and we can also use the precedence rule, as well as using the associative property. I know that you're familiar with the associative property and um, the precedence rule, and I'm a bit complacent pertains to that, since you already do have the foundation in terms of your mathematics during your elementary days. So in an expression tree, operands are the values or variables, and operators define the operations performed on those operands. The operators in the tree connect the operands, forming a mathematical expression. Say, for example, as what you have mentioned earlier, there will be like this, a plus b. How can we perform in terms of expression binary tree? It's actually a foundation for automata as well, because in automata we are dealing with parsing. So in parsing we are dealing with expression trees as well. So we're still working on with different with the same to the three-stage structure. However, it's there will be a little bit of difference. So, for example, in our expression tree, as what I mentioned, that operands must be in the leaf node, and then the operator will be the parent of that operands. So this is actually the representation for this one. This is the expression tree of this infix notation. But we'll begin to work on that with step by step, because there's a step by step on how to work on that one. Now, for the operands and operator and expression tree, let's try to deal with that. If you already forgot the what is operands and operators, since that was already discussed in your elementary days, and I know that grade one already know that this one is following. So identify operands. Operands represent the values or variables in the expression. These are the typically numbers, variables, or constants that the operators will act upon. So that means to say, in our infix notation, for example, you have here a plus b, then times c divide d, for example. So therefore, your operands right there will be the values itself. which will be the A, B, C, D only. Those are considered as the operands, which will be the value. It could be a number as well. It could be a character. Now, recognizing the constants and variable operands, so it can be like a number, like 3, or variables like a, x, and so on and so forth. These are the building blocks for the expression. In our expression, a plus b times 3, the operands right there will be a, b, and 3. So that is really basic, right? Now, dealing with identifying the operators, operators define the operations performed the operands such as addition, multiplication, or subtraction. This operator are crucial for determining how the operands relate to each other. So this is the connection between the operands. For example, what will be their connection? They do have a connection in terms of multiplication, which pertains to B and C. We can multiply that one, for example. And operators are symbols like plus and minus, times, or division that specify the operations to be performed on the operands. In the expression a plus b times 3, the operators are plus and the times. So that's how it works. That is actually basic. I've just included in this presentation so that you will really be aware for those things, since I know that some of you were maybe were able to forget the rules, or I mean the basic foundations of those things. Now, let's move on to the infix, prefix, and post documentation, so that you will also be aware. I know that some of you is not is not aware of this yet, so let's try to understand that first. So when we say infix and those notations, I mean, those are the mathematical expression that we can also denote that one in specific, those operations, I mean, can be written in infix, prefix, and postfix notation. So each notation actually represents how operators are placed in relation to operands, and is used differently in computations and parsing. So this is really one of the foundation, if especially if you are computer science, you must know how does it work logically. Since in parsing, if you're building your compiler, you must be aware how those notations work. There will be precedence rule that you will begin to observe as well. So in terms of trees, for the expression tree, we also need to be aware how the infix notation work. From the infix, we can actually transform that or convert that into the postfix, or it could be the prefix. So we can definitely understand this in a while. I know that it is somewhat vague right now, but of course we'll have to make it step by step. Now, in our infix notation, operators are placed between operands. This is the most common way of writing expression where the operators acts on the operands in the middle. So as when we say infix notation, always make sure to remember that in between, the relationship is in between. So for the expression a plus b times c, the operator plus is between a and b. And the operator multiplication is between a plus b and c. So in this one, if you will begin to evaluate this infix notation, if you're not using the precedence rule, since a plus, no, no, if you are, you can definitely understand if ever that A do have a value and B do have also a certain value and C do have certain value. So in calculating that one, you will go first with A plus B before going to times C, because that is actually having here the open and close parentheses. But if there's no open and close parentheses, we will have to follow the B times C first, then going to A plus B times C, since of course the precedence rules is following the PEMDAS, if you can still remember into your elementary days. Now, in this one, in prefix notation, from the infix notation, we can actually convert those specific notation into the prefix notation. And this is also known as the Polish notations. Operators are placed before their operands. That means to say the operators first before the operands. This removes the need for the parentheses to indicate the operation order as they operate as the operator's position dictates the order. For the expression a plus b times c, the prefix notation would be times plus abc, where the operator times comes from before the operands plus ab and c. So we'll be going to understand that in a while. We'll have to make it step by step so that it will not be vague for everybody. Okay. Now, in postfix notation, also known as the reverse Polish notation, or the RPN, operators are placed after the operands. That means to say that the operands will go first before they those value, variables, whatsoever. And this notation also eliminates the need for parentheses as the operator follows its operands. So for the expression a plus b times c, it must the postfix notation would be a b plus c times, where the operator plus comes from A and B, and times follows the result of A, B plus. So how does that work? Since as what we do have earlier, this is the expression that we're following, and this is the notations that we are having in our result. So we'll begin to understand that in a step-by-step manner as well. So, but before that, we'll have to understand as well the operator precedence and associativity rules so that we will know exactly how those work, if where to evaluate that, if it is for associative property, if it is left to right or right to left accordingly. So let's try to work on that. So operator precedence and associativity rules are essentials for determining the order in which operators are evaluated in an expression. Precedence tells us which operator has higher priority. So while associativity determines the direction of evaluations for operators of the same precedence. So that means to say, in our precedence and associativity rules, this will be the instrument for us to really know how it will be implemented, how it will be converted, those kind of notations that we do have. Now, operator precedence determines the order in which operators are applied in an expression. Operators with higher precedence are evaluated first, and the operators with lower precedence are evaluated later. So that means to say, for example, if we're following with the PEMDA, so what will be the highest, what will be the operators that do have the highest precedence? So that means to say the parentheses and going to the expression whatsoever, I know exponent, then multiplication, division, then addition and subtraction. That's how it works for the PEMDAS. Now, um, in our associativity as well, if there will be many, for example, there is a consecutive um, operators. For example, there in one notation there will be plus minus. So how will you interpret that one? How will you do it? So there will be actually a specific associativity rules that will begin to identify or will begin to based on that if it could be evaluated right to left or it could be evaluated from left to right accordingly. So let's try to understand that first. So the associativity determines the direction. So as what I mentioned, that is direction in which operators of the same precedence are evaluated. So the two main types are left to right and right to left associativity. So we have here actually a specific example in terms of working on this one or those PEMDAS that we do have, or those precedents that we do have, since as what I mentioned that the higher those having the highest precedence will be the parentheses, then going to the exponent, then the multiplication, division, and addition and subtraction. So therefore, the associativity here then will be this one. So for if ever that we're actually dealing in terms of exponent, we will be going to, since that is even the highest precedence among the common operator, so it will be evaluated from right to left associativity, meaning 2 to the power of 3 to the power of 4, it will be evaluated if you're beginning to calculate the manually. So it is like this: 2 third, then 3 may 4 pa na sa. So if you will be going to work on that from left to right, so 2 times 2 to the power of 3, if you'll begin to calculate that one, that is actually 2 times 2 times 2, that is 8, right? So I'm so sorry. That will become 8. Oops. Let me delete that one. Right. I'm sorry, I can't use my iPad yet because we're still working on their presentation. So then afterwards, 8 times 8 times 8 times 8, so that is 4 times, it will become 4,096 if we are working that one in terms of left to right. So if we're following the associativity direction, it must be 3 to the power of 4 first before going to that 2 to the power of what will be the um what we call this one result for this 3 to the power of 4. So assuming that 3 times 3 times 3 times 3 for the fourth time, here it will equate to 81. So that will become 2 to the power of 81. So therefore, if calculating 2 to the power of 81, it will be actually, let me just grab my iPad here so that I can easily calculate that one since I don't have the power to, I'm not Albert Einstein that can think really that much. So calculating the power rule, let me just, okay, so that is exponential calculator. Let's grab an exponential calculator here on my end first so that I can give you the correct answer for that one. So if we'll begin to calculate that 2 to the power of, um, okay, I can't see, okay, 2 to the power of 81. So that will equate to, check, 81. All right. So it will become 2.4 blah 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 and so on and so forth. So um it will be actually 2.4177 and blah 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 blah. So it's too long. So imagine from 4096 earlier, it is indeed different. So for example, 1 to the power of 2 and 2 to the power of 2. So if you will begin to multiply this from left to right, 1 times 1, it will become 1. Then times 1 times 1 again, so it will become 1 still for the left to right. But if you're going to right to left, so 2 to the power of 2, it will become 2 times 2, 4. Then 1 to the power of 4, it will become 1 times 1 times 1 times 1, it equals 1. So they are somewhat the same. However, the process is really different. Okay. Now let's proceed with multiplication and division. For the this is the second highest, having the higher, I mean the third highest precedence since the parenthesis is having the topmost priority. Okay, so multiplication and division have the second highest precedence just below exponentiation. So actually, it is the second highest precedence. So, my mistake. Both operations have left to right associativity, meaning we will begin to calculate that one from, if this will be the cases, 2 times 3 divide 4. So, of course, we can evaluate first 2 times 3 before going to the 3 divide 4. We cannot say the 3 divide 4 first, then going to the 2 times 3 because it will become, it is a violation in terms of the associativity function. So in our associativity rule, it must be evaluated from left to right accordingly. Okay, just always remember that one. So the answer for this, if you begin to carefully work on this, 2 times 3, it will become 6, divide 4. So definitely there will be point something. Okay, now for addition and subtraction, this is the having the lowest precedence. So addition and subtractions have the lowest precedence among the common operators. Both operators have left to right associativity, meaning 2 plus 3 minus 4 is evaluated as 2 plus 3 first, going to the minus 4. So that's how you will work on that, because you cannot just say 3 minus 4 first, then going to the 2 plus the result of 3 minus 4. No, that's not good. If ever that there will be a parentheses, always have the high, this is actually having the highest precedence, meaning any expression inside the parentheses is evaluated first, regardless of the operator outside. So this rule takes priority over all the operators. So if ever that there will be a specific calculation inside or notation inside that parenthesis, so you have to work on the parenthesis first, although that there will be exponent outside that parenthesis, but you need to really solve inside a parenthesis first. So for the expression 2 plus 3 times 4, the parenthesis, since the 2 plus 3 is enclosed with the parenthesis, so we need to calculate the 2 plus 3 before going to the multiplication. Because we cannot say that 2 times 4 first. Then where can we multiply that one, right? So yeah, I hopefully that you can really understand how does that work. So 2 plus 3 first, going to that times 4. So that's how it worked actually. Now, the parenthesis ensures that 2 plus 3 will be evaluated first, and then the result is multiplied to the 4. Now, we also do have here from the infix notation, we can convert that into the postfix notation only. The reminder, this is just absolutely the theory first. This is the introduction first before we'll begin to the expression 3. We're not on the expression 3 topic, okay? So converting infix to postfix notation is essential. For efficient evaluation in computers, postfix notation eliminates the need for parentheses and operator precedence rules, simplifying the evaluation process. So in converting infix to postfix notation, this is really essential since we will begin to eliminate the need for those parentheses and other operators precedence rule. So we'll begin to illustrate that in a while as well. So let's proceed. So infix to converting infix to prefix notation, it is useful for simplifying mathematical expression and for easier evaluation by computers. In prefix notation, the computer precedes its operands, removing the need for parentheses to dictate the order of operation. So we have to omit those parentheses. So here then, for example, start with infix expressions where we don't have parentheses here. So for example, if we have a plus b, then enclosed with the parentheses, you will begin to compare that actually. First, this one. So since in our prefix notation, the operator will go first, then A and B. Then afterwards, you will begin to compare this one, actually A plus B. Then you will convert that in this following structure because operator will go first, then the operands. So the operands will be in between to that infixation. Only that following expression, you will just base actually. So for example, A plus B enclosed with open parentheses and close parentheses. So you will begin to make this as plus AB and it will become times C right now. So now we do have two expression left. So plus AB enclosed with that one and this one. So we have to omit the open and close parentheses. It will become times, since times is the operands between the two expression, then copy this one, the first expression plus AB and the last operand, that is C. So therefore, the prefix notations of this infix notation will be times plus ABC. Let's try to see that one. So begin with the given infix expression. In this case, the example A plus B times C. It will be plus AB first, then going to the times C, so it will become still the same as like this. So in infix notation, operators are applied based on their precedence. Multiplication has higher precedence than addition, so multiplication will be performed first. So as what you have can see earlier, that multiplication is actually going first. Now to convert to prefix notation, place the operator before its operands. The higher precedence operator is placed first in the prefix expression, followed by the other operator and operands in the correct order. And then the final result is the expression in prefix notation where operators appear before their operands and the correct order of operations is maintained. So that's how it worked in the prefix expression. I mean notation. Now we also do have converting from the infix notation. We can also convert that into the postfix notation. Let's try to see how to work on that. So for infix to postfix notation, it will be like this. So let me just go ahead and go next. So we have to start with the infix expression. The first step is to take the infix expression that needs to be converted. In this case, we have example a plus b times c, for example. So the second step that we will need to consider will be moving from left to right, identify operands and operators. So we have to scan the infix expression from left to right. And when you encounter an operand, a variable or value, output that directly. So when you encounter an operator, prepare to process it based on operator precedence. So as what we do have earlier, we have A plus B, and then times the C. So how to work on that? So you have to work on this first because this is having the highest precedence. So it will become following the postfix notation. Postfix is actually basing on the operands first, then after the operators. So it will become A and B, then afterwards will be plus. So this is separate expression, and then we will continue. You have to do it step by step. So AB plus, open parenthesis and close parenthesis, you have to work that. This is one another expression, and this is also separate expression. So we can compare that too. So what we can do, AB plus and then times C. This is one expression, huh? So what we can do, it will become AB plus, then C multiplication or times. So this will be the postfix notation. So the next step for that accordingly, it will be converting the expression based on operator precedence. In postfix notation, operator follow their operands when encountering an operator. If it has lower precedence than the previous operator, output the previous operator first, then after encountering the operator and its operands, output the operator after all operands have been processed. So we have to work on that from left to right accordingly. Then final result is a postfix expression with operands and operators in the correct order for evaluation of evaluation. So don't you worry on that class because I'll be going to work on with separate video for the operation only, for converting of those notations so that you will really understand how to work on that step by step. Okay. Now for postfix the prefix notation, we can convert postfix to prefix accordingly. So for this one, for example, converting postfix to prefix notation is important for simplifying the expression and preparing it for evaluation in certain algorithms. And this conversion will eliminate the need for parentheses and operator precedence, ensuring the efficiency for evaluation. So this one, we have to start with the postfix expression. The first step is to take the given postfix expression. In this case, we have this one. So how to work from this postfix notation that we can convert into the prefix notation. So I'm so sorry. So it will become like this. Comparing first AB plus. So AB plus, it will become plus AB. Since AB is actually in between AB will be, we do have the operator as plus. It will become plus AB, then C multiplication. So this is another expression, and this is another expression. We can compare the two. It will become AB, C plus, and it will become multiplication. So that's how we work on that. So this is really so simple because we are comparing plus AB and C multiplication. So this is another set of expression. We cannot move this one already. So C will be in place, then we can just put this in the prefix place. Now, in postfix notation, identify operands and operators. In postfix notation, operands comes first, followed by the operators. Scan the expressions from left to right, and whenever you encounter an operator, the operands before it are combined to form a sub-expression in prefix notation. So that is really so simple. And replace operands with the new prefix expression. After processing an operator and its operands, replace the operands in the postfix expression with a newly formed prefix expression. So that is really simple. And continue converting the operators. Now repeat the process for the next operator in the expression. We continue scanning from left to right and combine the next operands with the operator to form a new prefix expression. So as what we have identified earlier, that's how the step-by-step process for this one. And then the last part will be the final prefix expression. After processing all the operators and operands, the final result prevails. So how to work on this one right now? Prefix, I mean, those are the expression, the conversion, how we're able to achieve that earlier. You have to take note that one. Don't you worry because we'll begin to give another set of examples later on. Let's proceed with the prefix to postfix notation because in prefix to postfix notation, we can definitely calculate that one. Also, we can make sure to do it step by step. Okay. So for this following expression here, converting prefix to postfix notation is important for evaluating expression efficiently. In prefix notation, operators precede their operands, while in postfix notation, operators follow their operands. So that's how it works. So start with the prefix notation. Begin with a given prefix expression that needs to be converted. The example will be like this. So from this one, we will be going to work on with we'll begin the expression since this is our expression right now that we'll begin to convert. So let's try to work on this carefully. So let's go ahead and check the next step. Okay. Okay. Now, identify the operators and operands. In prefix notation, the operator always comes first, followed by the operands. Scan the expression from left to right, and when you encounter an operator, apply it to the operands that follow it. So from this one, it will become plus A. So therefore, it will become A plus A. Then there is times BC. So what will be the expression that do have the highest precedence right there? It will be the multiplication, right? So we'll begin to see it accordingly. How can we work on this one? So suppose this is another set of expression and this is another set of expression. So A will become plus A plus it will become times then B C plus. We can perform that like this. So this is another set of expression, the A, and then this is a set of another expression. So we can perform as A, B, C plus multiplication. I'm not really sure if this is, yes, this will work. We'll try to see this one. So in prefix notation, for each operator, place the five operands after the operator following the rules of postfix notation, where the operator comes after the operands. So the final result is the expression in postfix notation, where all operators are placed after their operands. So that's correct earlier. So in these structures, since we're able to compare A times BC, then plus, so it will become ABC plus multiplication. But if our operands will be like this, times, our prefix is like this, times plus ABC, as what we do have earlier. So we can work on with plus first, times first, then with this one. So it will become plus, It will become, another operation will be this. So postfix. So C become plus and A, B, then C, then multiplication here. So suppose that we are, because this is actually the expression in between earlier, the operands that we are basing is AB and C, correct? So this is in between the multiplication. So we can say, because it's one from right to left. So here then, we have left AB, and that is in between of this one. Okay, so it will become A, B plus, and C multiplication. So this is the postfix notations from this expression. But this is different because plus A, we can compare that into the BC accordingly. So it will become A times, no, A times BC plus, then afterwards, we'll compare this A, no. Yeah, compare this B and C. So B and C having in between multiplication. So it will become um, ABC, ABC, no, A, B, C. So in between earlier is B and C, right? So BC times. So therefore, there is another set of, this is included into your notation earlier. So it will be at the last part. So plus multiplication. So this is really how it works. So hopefully that is clear for everybody. But of course, that's not the expression 3 yet, okay? So expression 3 will be really basic. I am just discussing how you're able to convert those notations only. This is actually the introduction part. Now, let's try to work on with the components of an expression tree. So the components of expression tree is consisting of two components: operators in the internal nodes and operands, values of or variables in the leaf node, and expression will in the expression A plus B times C. So times is the having the highest precedence, and then plus are operators as well. So they are the operators here, and then this is the operands that we do have. So since, as what we mentioned, that the leaf node in our expression tree will be the operands, then the operators will be inside. It will become the internal nodes, and afterwards, in an expression tree, the root node represents the main operator, the left and right children represent the sub-expression, and the leaf nodes represent operands. So in our expression class, by the way, just try to take note that having the what will be going to serve the root node is actually those element, or I mean those expressions that do have the lowest precedence. So we'll begin to work on that later on how you will begin to work on using, because there will be two ways: using the stack implementation and using the precedence rule. Now, for example, for A plus B times C, the three structures would look like: the root node will be for example, A plus B. So this is actually different, okay? Because A plus B is having the highest precedence, so times C is lowest precedence right now. So here, the lowest precedence is C. C then over this will be the left sub tree, and this will be the right sub tree. So it will become C. Then here will become A plus B, and this one. So their root node is the multiplication. Now afterwards, we will work on this one. How to work on that one? We will begin to, that is the left subtree, it will become like this: A, B, and then their root node is plus. So this is the expression tree of this following example. But if we're working with A plus B times C, it is also different because their having the lowest precedence right now is the plus. So therefore, plus will be evaluated first. So plus, then AB. And then times C is actually in your, no. What, what will gonna happen? I'm so sorry. We have to work on from highest precedence. Since PEMDAS, right? PEMDAS. Have to work on with the highest precedence. Ups. I'm so sorry. That. Okay. Who do have the highest precedence right now in this following structure? So earlier, um, we're supposed to go first to the highest precedence, so that is A plus B. So this is this one. And after A plus B, times C is the lowest precedence, so we can definitely put this one above. So times will be the root node. Then afterwards, if this will be the case, the lower precedence right here is plus. Plus. So therefore, highest precedence will be times. So we can work on that one, times. And those highest precedence will be placed at the almost at the bottom part of your tree. So this is A, and no, this is B, and this is C. So the left subtree will be the plus and A. So therefore, there, this one, B plus C, is plus then A. So therefore, this is the tree, particular expression tree of this following structure. So that's how you will work on this one. Hopefully that you're able to understand that one. That is actually based on the precedence rule. Now, the steps in constructing using an expression tree, we identify the operators and place them as internal nodes. Operators are the building blocks of the expression tree and should be placed at the internal node, and these operators connect the operands and determine the structures of the tree. Afterwards, place operands, values, or variables in the leaf node. Operands such as the variables or constants are placed in the leaf nodes of the tree. They serve as the values that the operators will act upon. So as what we have mentioned earlier, that the operands must be placed at the leaf node. Then afterwards, the operator precedence determines the structures of the tree. The structures of the expression tree is influenced by operators precedence, which ensures the higher priority operations are presented higher in the tree, and that guarantees as well the operations are performed in the correct order. So we have to perform the highest precedence and place that at the bottom part, and then going to the upper part will be those lowest, having the lowest precedence. So the operation and expression trees. Talking to operation, it will allows us to perform various operations such as the evaluation, simplification, and conversion to other notations like the postfix or prefix. So there will be many conversion of that will gonna happen in this expression. So these operations are essential for computational tasks like evaluating expression and optimizing the formulas. So that's actually what will gonna happen for this. And the step that we have, this is for the evaluating the expression tree. Evaluation of expression tree involves the traversing the tree and performing the operations defined by the operators at each node. So using the operands at the leaf node, the tree is evaluated recursively from the leaves to the root. So that's why that's how it works. So for example, the operands is A plus B, then their precedence is having the multiplication that is actually having the highest precedence. So we can work on that first, and it will be put at the lowest level into your expression tree, and then we can work on with those lower level, and then it will become the root node afterwards if ever. It depends on how we evaluate that later on. Don't you worry, we'll begin to work on that in a while in different video also, so that it will be clear. This is actually the theory here. Now, for example, the expression tree representing A plus B times C. So for having the highest precedence will be A plus B. So we can evaluate the sub-expression A plus B, then multiplying that into this C. We cannot multiply this particular A plus, B times C, because this is different, because this is enclosed with open and closed parentheses. We cannot follow the PEMDAS for that one. Now, simplify the expression tree. Simplification involves reducing the expression by applying algebraic rules like combining like terms or eliminating redundant operations. the tree is traversed and simplified at each step. So in simplifying the expression actually, for the expression a plus b, we can simplify a plus b first, then going to the plus c. So apply the associative property from left to right. Since the precedence rule mentioned that we can work on with a plus b and that is left to right accordingly, then afterwards we can also assess that adding that into the c. So this simplifies the expression by grouping terms in a more efficient way depending on the context. So that is really basic. I hope hopefully that you were able to really understand how what I mean, since that is for elementary level only. Now, convert expression 3 to prefix expression. So this is the conversion that we'll begin to identify later on. So to convert the expression 3 to prefix expression, to traverse the 3 in the prefix order, like operator, left sub 3, right sub 3, and place the operator before its operand. So here then, we will begin to work on with, since we're working with the prefix operation, so we will begin to work on with the highest precedence and then going to the lowest precedence, and lowest precedence will be the topmost in our tree. So to convert the expression 3 to postfix notation, traverse the 3 in the postfix order, left sub 3, right sub 3, and then operator, and write the operands followed by the operator. So this is how we'll begin to, this is the things that we can consider as well, that we can also convert expression 3 to postfix notation, so that we can also see if what will be the expected postfix that we can perform. But of course, that is for the checking, but I'll begin to show you the step-by-step process that you have to follow then. Okay, I'll begin to explain to everybody in the spread video the process of those conversion, and then the process of creating expression tree from postfix using the stack. We can perform that one actually. But here then, allow me to discuss first all of the what we call this one, the deliverables first before going delving into that operations. Okay. So expression trees are widely used in compilers, solvers, mathematical expression evaluation. They simplify the representation of expression and make the evaluation process more efficient. Expression trees for expression parsing and compilers. Um, Compilers use expression trees to parse and understand mathematical and logical expression. That these structures helps break down complex expressions to simpler parts, which are easier to evaluate and are optimized during the compilation process. So in that instance, if you are studying automata, it will be actually discussed there once you will begin to search once you will begin to switch, or I mean once you will begin to um, if ever that you may have a a like if you're having a what do you call this one, like you wanted to switch into the computer science student, you can definitely um, learn more about parsing technique. So trees for expression trees for simplifying expression in solver. In mathematical solver, expression help also to simplify and evaluate algebraic expression. The tree structures allow for efficient simplification by reducing the sub-expression and applying algebraic rules recursively. Afterwards, we are using expression trees for efficient expression evaluation, allow for efficient post-order traversal, which evaluating expressions from the leaves of pronouns upwards. This method is ideal for evaluating complex expression in a systematic way. And we are also using in for algebraic expression, manipulation and optimization. It can be used to manipulate and optimize algebraic expression by using three traversal techniques. Can be simplified, redundant, operation can be removed, and common sub-expression can be factored out. After that one, used in symbolic computation and mathematical libraries. Expression trees are used in symbolic computation tools and mathematical libraries to handle complex operations symbolically, um, enabling efficient computation, differentiation, and simplification. So there will be disadvantages of expression as well. While expression trees are powerful tools for representing the and evaluating expression, they come with certain drawbacks. This include increased memory usage and complexity as well, because this is really hectic to work on. Include increase of memory usage and complexity when dealing with large or deeply nested expression trees also demand more computational resources compared to simpler data structures. So in this actually instance, there's a lot of calculations. There's a lot of um, process that you will begin to work on. That's why it's taking a lot of time. And consider alternatives for smaller expression. If smaller expression only, your expression tree is not really useful. Expression trees may not be necessary. Using simpler data structures like arrays or linked list can reduce overhead and improve performance. So since every element do have specific memory usage, of course, definitely will begin to there's the memory will be there will be allocations, and it is really a waste, definitely wasteful of time, waste everything will be wasted. So increased memory usage. Each node in the expression tree requires additional memory to store the operator or operand, which can lead to high memory consumption, especially with large expressions. So this is not really good because each even a single operator or operands definitely there is a memory allocations that we need to work on. And afterwards, complexity with large or nested expression. Managing large or deeply nested expression can become inefficient because due to the space complexity that it is linear time. All of those things needs to have allocated spaces. So the process of traversing for this will become or modify these trees in real-time application can slow down performance and increase algorithm inefficiency complexity. So be cautious of memory usage with large expression. When dealing with large or deeply nested expression, memory usage can increase exponentially. It's important to be aware of the memory limitations of the system to avoid running into issues like stack overflow or out of memory errors. So in this instance, actually, this is just useful for if you wanted to understand how does the algebraic expression to be expanded or the parsing expression if you're working with compilers or programming languages, so it might be a big help. So the impact on performance in real-time application, the complexity of managing and evaluating large expression trees can reduce overall system performance, and this is particularly problematic in scenarios requiring quick computations. If you are likely wanted to have quick approach or lookup of operations, so this is really not good as well, since it will take a lot of time, linear time. And there will be advantages aside from this, the disadvantages that I have explained to to you. So offers several advantages in mathematical computation and expression evaluation. They provide a clear and efficient way to represent complex expression, enabling faster evaluation and easier manipulation. What are those? It can be simplified by expression by breaking them into manageable expression, sub-expression, wherein expression trees simplify complex expression by breaking them down into smaller parts. Manageable sub-expression, each subtree can represent a part of the overall expression, making it easier to manipulate and optimize. Afterwards, it can optimize also the algebraic expression where we can understand and we can simplify everything. How does that work? And can be used to optimize the algebraic expression by rearranging the nodes for more efficient computation. Includes the factoring like terms and applying algebraic identities. This is really simple actually. And the time complexity and space complexity for this one, this will be depending on their size of and operation as well. Offer an efficient way to evaluate expressions, but there are performance considerations that we have to keep in mind. So for example, for building the tree, the time complexity for this one it will be linear because there will be such allocations that we will begin to to allocate specific operands and operators accordingly. So the time complexity for that will gonna be the linear time wherein is the total number of operands and the operators in the expression. This is because each operand operator is process one. So as what I have mentioned to you that we are allocating every process. So the time complexity for traversing the tree will still be linear time because you will begin to check that one level by level, and that is definitely if you will begin to do it in order traversal, pre-order traversal, and post-order traversal. So of course that is still linear time because you will be going to visit and do the backtracking as well. up until such time that you were able to certainly check or visited all of the elements. Now the space complexity will also be linear because the expression tree where n is the total number of nodes, operands, and operators. This is because the tree requires space to store each node. So as what I have stated, that all of the operands and operators do have the separate allocations of memories. So that's the end of our discussion actually. And always make sure to remember that the creation of thousand forests is in one acorn. So according to Ralph Waldo Emerson, means that even in the smallest actions or beginnings, we do have also the potential to lead to something much larger and more impactful as well. Just like an acorn, which is having the small and simple, it can grow into a vast forest over time. So small efforts or humble beginnings can definitely lead to greatest achievements. So make sure to really work on, make sure to really understand the process accordingly, step by step, nugget niya for me. Okay? So hopefully that you were able to understand the process, and I'll begin to illustrate in the separate video all of the calculation process, because this in this video I have actually illustrated all of the theories. So I'll begin to explain as well the theories for those process for the conversion and separate videos so that you will really understand how we're able to establish or process that one. Okay, so in this video class, in order for you to in order for me to assess that you were able to work on and understand the process, the theories, so make sure to put a certain comment for your attendance, and for this is part of your quiz as well. And you have to comment at least 2 sentences, and that is equivalent to 5 points. And all of your answers in based on your understanding, based on your own interpretation, based on the discussions that I have presented to you in this video. If you failure to put a comment will lead to 0 into your into this certain question. Okay, so make sure that you are not having the same answer with your classmate, because having the same answer and having a answer of AI generated will result to 0 as well, failure. So make sure to really be persistent in terms of working and understanding in terms of this expression tree, because this is really the complicated tree that you will begin to learn, and that you will begin to remember as you go through with the final examination. Make sure to really understand the process, okay? Don't you worry, I'll begin to picture out the process, the calculations in the separate video. See you there. Goodbye.